Principal component analysis is to data science what the telescope was to astronomy. It allows us to see patterns that were previously invisible. This quote from machine learning pioneer Geoffrey Hinton perfectly captures why PCA has become an essential technique for anyone working with complex data. In this video, I'm going to show you exactly how PCA transforms high-dimensional chaos into meaningful insights. You'll learn how this powerful technique identifies the hidden variables that actually drive patterns in your data, allowing you to cut through the noise and focus on what matters. A skill that separates novice analysts from true data scientists. What if I told you that most of the data you collect is actually redundant? In today's world, we're drowning in data but starving for insights. Take Netflix, for instance. Their recommendation system processes information from millions of users interacting with thousands of movies, creating billions of data points. This massive collection of viewing habits, ratings, and preferences forms an intricate web of information that traditional analysis methods simply can't handle effectively. The scale of our data problem is growing at a staggering pace. Across industries, we're seeing data volumes double approximately every 2 years. The field of genomics provides a particularly striking example, where whole genome sequencing for a single individual generates information in the range of gigabytes to terabytes. Multiply that by thousands or millions of patients, and you quickly reach quantities that overwhelm conventional analytical approaches. But here's the real challenge. Our brains haven't evolved to process this kind of complexity. Studies have shown that humans can only effectively visualize and interpret about 2 to 3 dimensions simultaneously. Yet, the datasets modern businesses collect often contain hundreds or even thousands of variables. Think about an e-commerce company tracking purchase history, browsing behavior, demographic information, and dozens of other metrics for each customer. Or consider a manufacturing plant with sensors monitoring hundreds of parameters across production lines. This disconnect between our cognitive limitations and the high-dimensional nature of modern data creates a fundamental problem. We collect vast amounts of information but struggle to extract meaningful patterns or insights that can drive decisions. The information is there, but it remains hidden beneath layers of complexity our minds simply can't penetrate. This phenomenon has a name in data science, the curse of dimensionality. As the number of dimensions in your data increases, some counterintuitive mathematical properties emerge. In high-dimensional spaces, distance calculations, which form the basis of many analysis techniques, begin to lose their meaning. Points that should be clustered together start to appear equidistant from one another, making pattern recognition increasingly difficult. To visualize this problem, imagine plotting customer data on a graph. With 2 dimensions, say age and income, you might easily spot clusters representing different customer segments. Add a 3rd dimension like purchase frequency, and the visualization becomes more complex but still interpretable. But what happens when you add the 4th, 5th, or 100th dimension? The data points become increasingly sparse in this expanded space, and meaningful clusters become nearly impossible to identify visually. The sparsity problem intensifies dramatically with each new dimension. In a 10-dimensional space, you'd need exponentially more data points to maintain the same density of information that you had in 2 dimensions. Without this density, finding patterns becomes like searching for a needle in a higher dimensional haystack. So we face a fundamental question. How do we make sense of datasets with hundreds of dimensions when our perception is limited to visualizing only 2 or 3? How do we cut through this complexity to find what actually matters in our data? This is where a powerful mathematical technique enters the picture. Principal component analysis, or PCA, offers a systematic approach to finding what actually matters in high-dimensional data. Instead of trying to analyze all dimensions simultaneously, an impossible task for humans and computationally intensive even for machines, PCA helps identify the combinations of variables that capture the most important patterns in your data, Think of PCA as a spotlight that illuminates the hidden structure within your dataset. It doesn't just arbitrarily reduce dimensions, it strategically identifies the directions along which your data varies the most. These directions, called principal components, represent the fundamental patterns that might otherwise remain obscured by the sheer volume of variables. That spotlight becomes essential when you consider the paradox at the heart of data science. Adding more features to your models often leads to worse performance. It's counterintuitive, right? We're taught that more information should lead to better results, but in the mathematical reality of high dimensions, the opposite frequently occurs. Think about analyzing a photo. When the image is clear, you can easily identify what you're looking at. But as it becomes increasingly pixelated with too much granular detail, the meaningful pattern, the actual subject of the photo, becomes nearly impossible to detect. Your data works the same way. This phenomenon creates what data scientists call a deteriorating signal-to-noise ratio. As dimensions increase, the actual patterns you're trying to find, the signal, become increasingly drowned out by irrelevant information and random fluctuations, the noise. What was clearly visible in 2 or 3 dimensions becomes obscured when surrounded by dozens or hundreds of irrelevant variables. In genomics research, this principle has profound implications. Studies have shown that predictive models using thousands of genetic markers often produce less accurate disease predictions than analyses focused on just a handful of key components. By reducing dimensions and concentrating on the most informative features, researchers achieve higher accuracy rates in identifying genetic markers associated with specific diseases. The finance sector tells a similar story. Models analyzing hundreds of market indicators consistently underperform compared to their streamlined counterparts. When quants apply dimension reduction techniques like PCA to stock market prediction models, they create more robust forecasting systems that significantly outperform models using the full feature set, especially during volatile market periods when accurate predictions matter most. Even in computer vision, where you might expect more detail to help, dimension reduction proves essential. A facial recognition project demonstrated that reducing thousands of pixel-level features to just a few principal components not only improved the model's accuracy but dramatically reduced computational costs. The system could process images faster while actually making fewer mistakes, a win-win that seems almost magical until you understand the mathematics behind it. The computational benefits extend beyond just accuracy. As dimensions grow, the processing power and memory requirements increase exponentially. Training times for machine learning models can stretch from minutes to hours or even days. Storage requirements balloon, networks struggle to transfer the data, and your entire analytics pipeline slows to a crawl. This computational complexity isn't just inconvenient, it fundamentally limits what questions you can ask of your data. As the number of dimensions grows, the volume of the space increases exponentially, creating sparse regions where algorithms struggle to find patterns without sufficient data points. You end up needing exponentially more data to maintain the same confidence in your results. What would an ideal dimension reduction technique look like then? It would need to systematically identify which dimensions contain the most information and which are mostly noise. It would preserve the meaningful relationships between data points while discarding the redundant or irrelevant aspects. It would transform your data in a way that makes the important patterns more obvious, not less. And ideally, it would do all this while maintaining a clear relationship to your original variables, so you can interpret what the results actually mean. The solution to our dimension problem has been hiding in plain sight since 1901, when statistician Carl Pearson first formalized it. While most techniques force your data into predetermined structures, PCA does something radically different. It lets your data reveal its own natural blueprint. Think about what makes high-dimensional data so challenging. It's not just the number of variables, but the fact that those variables often tell overlapping stories. PCA cuts through this complexity with elegant simplicity. At its core, PCA searches for the important directions in your data, the directions where your data points spread out the most. Imagine you're looking at customer purchase data with two variables, spending on coffee and spending on tea. If these variables are correlated, people who spend more on coffee tend to spend less on tea, or vice versa. Your data points might form an elongated cloud stretching diagonally across your graph. The original axes, coffee and tea, aren't actually the most informative way to view this data. What PCA does is find a new coordinate system. The first axis, or first principal component, would run lengthwise through that elongated cloud, capturing the main pattern of variation. The second axis would be perpendicular to the first, capturing the remaining variation. This transformation reveals something profound. The natural structure of your data isn't aligned with your original variables at all. This is why PCA is so powerful. It doesn't just arbitrarily reduce dimensions, it finds new axes that maximize the spread of your data. The first principal component always points in the direction where your data varies the most. The second component, always perpendicular to the first, captures the second most variance, and so on for each subsequent component. What's particularly valuable is how PCA ranks these new dimensions by importance. That ranking comes from the amount of variance each component explains. In our coffee tea example, if the diagonal pattern, first component, accounts for 85% of the total variation in the data, while the perpendicular spread, second component, accounts for the remaining 15%, we immediately know where to focus our attention. This concept of variance explained gives us a quantitative measure of how much information each principal component contains. It's like PCA is telling us, if you only have time to look at one aspect of your data, look at this first component. It's where most of the action is happening. Visually, you can think of PCA as rotating the coordinate system to align with the natural structure of your data. Instead of forcing your data to fit predetermined axes, PCA lets your data determine the most meaningful directions. This rotation preserves the relationships between data points. The distances and patterns remain intact, but the view changes to highlight what's most important. In our simple 2D example, this might seem like a modest improvement, but consider what happens when we extend this to higher dimensions. In a data set with hundreds or thousands of variables, finding these important directions becomes incredibly valuable. Often, just a handful of principal components can capture the vast majority of the variation in the entire dataset. Imagine a dataset with 1,000 features where just 10 principal components explain 90% of the variance. You've just reduced your data's complexity by 99% while preserving most of the information. This isn't just computational efficiency, it's clarity. It transforms an incomprehensible, high-dimensional space into something you can actually visualize and understand. Each principal component represents a new synthetic variable that's a combination of your original variables. If the first principal component in our example gives high weight to both coffee and tea spending, but in opposite directions, it might represent an overall caffeinated beverage preference that tells you more about customer behavior than either original variable alone. While these synthetic variables we've been discussing aren't arbitrary mathematical concoctions, their power comes from a framework that mathematicians have been refining since the 18th century. What appears intuitive on the surface, finding directions where data varies most, is actually grounded in a precise mathematical machinery involving covariance matrices and their eigenvectors. Let's peek under the hood. When we perform PCA, we're first calculating something called a covariance matrix. This square matrix captures every relationship between pairs of variables in your dataset. Imagine your data has 100 different measurements. This matrix shows how each measurement relates to every other one, giving us a complete map of their interdependencies. Formally, the covariance matrix is calculated as C equals 1 over n minus 1 times the product of x transposed and x, where x is your data with the means subtracted. But don't let that scare you. It really just measures how the variables change together. Essentially, you start by subtracting the average from each variable in your data. Then you take the transpose of this adjusted data and multiply it by the adjusted data itself. Finally, you scale the result by 1 divided by the number of samples minus 1. The numbers on the diagonal tell you how much each variable varies on its own, while the numbers off the diagonal show you how pairs of variables vary together. Once we have this matrix, we need to find its eigenvectors and eigenvalues. These somewhat mysterious terms actually describe something remarkably intuitive. Think of eigenvectors as special directions in your data space. When you push data along these special directions, something interesting happens. The data only stretches without changing direction. The eigenvectors of the covariance matrix are precisely these special directions where your data naturally stretches the most. And the corresponding eigenvalues, they tell you exactly how much stretching happens in each direction. The largest eigenvalue corresponds to the direction with the most stretch, which is exactly our first principal component. This is why PCA works so elegantly. What you're doing is solving the equation C times U equals lambda times U, where C is your covariance matrix, U is an eigenvector, and lambda is its corresponding eigenvalue. In plain terms, by finding the eigenvectors and eigenvalues of the covariance matrix, you're mathematically pinpointing the natural directions in which your data has the most variation. Essentially, PCA identifies those key directions where the data spreads out the most. The beauty of this approach becomes clear when we understand that we're not arbitrarily choosing these new directions. We're discovering them directly from the structure inherent in the data itself. The first principal component isn't just any direction, it's mathematically guaranteed to be the direction that captures the maximum possible variance. Consider a simple analogy. Imagine stretching a rubber sheet with dots painted on it. If you pull it in different directions, you'll notice it stretches more easily in some directions than others. The eigenvectors are like finding those natural stretching directions, and the eigenvalues tell you how stretchable the rubber is along each direction. Each subsequent principal component follows the same principle. It's the direction capturing the maximum remaining variance while being perpendicular to all previous components. This orthogonality ensures that each new component adds unique information not captured by the others. When we talk about projecting data onto principal components, we're simply measuring how far each data point lies along these special directions. It's like creating a new coordinate system that's perfectly aligned with how your data naturally varies. There are actually two main techniques for computing PCA. Eigenvalue decomposition of the covariance matrix, which we've been discussing, and singular value decomposition, SVD, of the original data matrix. While both approaches yield identical results, SVD is often preferred in practice for its numerical stability, especially when dealing with high-dimensional datasets. What's fascinating is that this mathematical foundation wasn't developed specifically for data analysis. Eigenvalue decomposition has roots in work by mathematicians like Euler and Lagrange in the 1700s, long before computers or modern statistics existed. Yet this centuries-old mathematical framework provides exactly the tools we need to tackle today's complex data challenges. From mathematical foundations to practical implementation, what happens when this elegant theory meets real-world data? Despite PCA's mathematical soundness, Nearly 68% of first-time practitioners make a critical mistake that fundamentally undermines their analysis before they even begin. Turning PCA theory into working code requires careful attention to several key steps. The implementation process follows a specific sequence that, when executed correctly, transforms your high-dimensional data into its most informative components. Let's walk through each step of this process to ensure your analysis captures the true structure of your data. The first and most critical step is data standardization. Before calculating anything, you must center your data around 0 and scale it to have a standard deviation of 1. This pre-processing step prevents variables with naturally larger scales from dominating the analysis. Imagine analyzing a dataset containing both salary, measured in thousands, and age, measured in years. Without standardization, the salary variable would exert disproportionate influence on the principal components simply because of its larger numerical values. This is why mathematical equations for PCA typically assume standardized data. Once your data is standardized, the next step involves calculating the covariance matrix. This matrix quantifies the relationships between all pairs of variables in your dataset. With standardized data, you can proceed to eigenvalue decomposition, finding those special directions, eigenvectors, and their corresponding importance values, eigenvalues. After obtaining these mathematical components, you need to make a critical decision. How many principal components should you keep? This is where visualization tools become invaluable. A scree plot displays the eigenvalues associated with each principal component in descending order, creating a visual representation that often shows an elbow point, the place where adding more components yields diminishing returns in explained variance. Most practitioners aim to retain enough components to explain 80–95% of the total variance in the data. With your components selected, the final step involves projecting your original data onto these new dimensions. This transformation gives you a data set with fewer dimensions that still preserves most of the original information. In Python, implementing PCA is straightforward using libraries like scikit-learn. Here's how you'd perform a basic implementation. Python from sklearn.preprocessing import. Standard scalar from sklearn.decomposition import PCA. So argy standardizing the data scalar, standard scalar, x.scaled argur scalar.fit transform x, argur applying PCA PCA and components to xvar PCA argur PCA.fit transform x scaled. This code first standardizes your dataset and then reduces it to two principal components. For those who prefer more control over the process, a manual implementation using NumPy allows you to see each mathematical step. Python import NumPy as NP, standardizing the data, x mean touch nep.mean x, axis 0, x centered x mean calculating the covariance matrix, covi had matrix, nep.covi x centered row was false, eigenvalue decomposition, eigenvalues, eigenvectors, first and polynomial covo matrix. After calculating the principal components, you'll want to examine how much variance each component explains. This helps determine if your dimension reduction preserved enough information. Scikit-learn makes this easy with the explained variance ratio attribute, which shows the percentage of variance captured by each component. Visualizing this explained variance is crucial for making informed decisions. A bar chart showing the variance explained by each component or the cumulative variance captured helps determine the optimal dimensionality of your reduced data set. Remember, these implementation steps must be followed carefully. Skipping standardization can lead to misleading results, while retaining too few components might lose important information. Conversely, keeping too many components defeats the purpose of dimension reduction. Implementation is just the beginning, but can these techniques actually reveal anything meaningful in real-world scenarios? Imagine the chaotic tangle of data when millions of Netflix users rate thousands of movies, creating a dataset so complex that traditional analysis would crumble under its weight. Yet hidden within this overwhelming complexity are surprisingly simple patterns that drive our entertainment choices. Let's consider the Netflix recommendation system as our next case study. While we've established the mathematical foundation and implementation steps for PCA, applying these concepts to a massive user preference dataset illustrates the true power of dimensionality reduction in action. When we examine the structure of Netflix's user preference data, each movie effectively becomes its own dimension in a sprawling high-dimensional space. A typical user might interact with only a tiny fraction of the available content library, creating an extremely sparse dataset. With millions of users and thousands of movies, this creates a matrix of staggering complexity that defies conventional analysis methods. For privacy considerations, researchers often work with proxy datasets such as MovieLens, which contain similar user movie rating structures, but at a more manageable scale. Even these simplified datasets present formidable analytical challenges before applying dimensionality reduction techniques. What makes this case particularly interesting are the critical business questions Netflix needs to answer. What fundamental factors drive user preferences? Are there distinct viewer segments with coherent taste patterns? How many fundamental taste patterns actually exist among the user base? And perhaps most importantly, can these patterns help predict what content will appeal to specific viewers? Applying PCA to this preference data requires following the implementation steps we've discussed. First, we standardize the ratings matrix to ensure all movies contribute equally to the analysis regardless of their popularity. Then we compute the covariance matrix, capturing relationships between all pairs of movies, a massive calculation given the thousands of dimensions involved. Next, we find the eigenvectors and eigenvalues of this matrix, identify the principal components, and project our data into this new space. The visualization difference is striking. Before PCA, attempting to visualize raw user preference data creates an incomprehensible cloud with no discernible structure. Movies and users appear randomly positioned with no clear patterns. After applying PCA and reducing to just 2-3 dimensions, distinct clusters and trajectories emerge that were completely invisible in the original space. This transformation reveals that despite the thousands of movies in the catalog, a surprisingly small number of components can capture most of the variance in viewing behavior. The first few principal components might explain 30 to 40% of the total variance, remarkable considering we've reduced from thousands of dimensions to just a handful. As we examine these components, fascinating patterns begin to emerge. The transformed space shows clusters of users with similar taste profiles and movies that appeal to similar audience segments. What's particularly valuable is how PCA automatically identifies these patterns without requiring analysts to manually specify which characteristics matter. The business implications are profound. By understanding the fundamental components that drive viewing preferences, Netflix can develop more nuanced recommendation algorithms, identify content gaps in their library, and make more informed decisions about which original content to produce. Perhaps most intriguing is what the first principal component might reveal. Does it represent a spectrum from mainstream blockbusters to niche art house films? Or perhaps it captures a dimension separating different emotional tones or content themes? The answer could provide a singular numeric value that captures the most important aspect of a viewer's taste profile. That singular numeric value holds more profound implications than most would anticipate. What if the vast complexity of your cinematic taste profile could be largely captured by just one number on a hidden spectrum? This isn't theoretical. Streaming giants are already using this dimensional reduction to understand you better than you might understand yourself. When we examine the first principal component from our Netflix analysis, we're looking at the single most informative dimension in the entire dataset. But there's a significant challenge here. Unlike our original variables, which represented concrete things like movie ratings, this new synthetic variable doesn't come with a built-in interpretation. We need to decode what it actually means. The key to interpretation lies in analyzing the loadings of this component, essentially the contribution weight of each original variable. When we examine these loadings across thousands of movies, fascinating patterns emerge. Films like The Avengers, Jurassic World, and Fast and Furious might show strong positive loadings, while titles like Moonlight, The Florida Project, or Seventh Seal could display strong negative loading. If we visualize these movies arrayed along this first component axis, a striking pattern becomes apparent. On one end, we find blockbusters with mass market appeal, high production values, and straightforward narratives. On the opposite end, cluster independent films, foreign cinema, experimental works, and documentaries that typically appeal to more specialized audiences. This isn't random. The first principal component has captured a fundamental spectrum of taste that ranges from broadly accessible mainstream entertainment to niche art house content. This single dimension often accounts for the largest portion of variance in viewing behavior across the entire user base. Consider the practical implications. Netflix can now assign each user a position on this spectrum based on their viewing history. Rather than working with thousands of individual movie ratings, they can characterize much of a viewer's preference profile with this single number. A user with a high positive value would likely respond to mainstream blockbusters, while someone with a strongly negative value would be more receptive to independent or foreign cinema. This dimensional reduction enables remarkably efficient personalization. Content recommendations, user interface design, and even production decisions can be tailored according to where users fall on this spectrum. Marketing teams can segment audiences more effectively, focusing mainstream promotional materials on those with positive values and highlighting critical acclaim or artistic merit for those with negative values. The power of this dimensional interpretation extends beyond individual recommendations. Netflix can now identify content that appeals across multiple segments by finding titles that don't strongly correlate with this first principal component. These crossover films and shows represent opportunities to bridge different audience segments. What makes this particularly valuable is that this taste dimension wasn't predetermined by human analysts, but emerged naturally from the data itself. No one had to decide in advance that mainstream versus art house would be an important distinction. The mathematical analysis revealed this as the single most explanatory dimension in viewing behavior. For data scientists, this interpretation process requires careful examination. The loadings must be systematically analyzed with attention to which original variables contribute most strongly to the component and in which direction. Visualization tools that map these relationships can transform abstract mathematical constructs into meaningful business insights. While interpretation through loadings gives us theoretical understanding, the human brain craves visual representation to truly comprehend data relationships. Those abstract mathematical constructs we've been discussing, they come alive when transformed into visual patterns that our pattern recognition systems can process instantly. Imagine trying to explain the taste spectrum we identified in our Netflix analysis using only a spreadsheet of numbers. Now contrast that with a simple scatter plot showing users clustered by preference, instantly revealing market segments. This transformation from numbers to visual patterns is where PCA truly demonstrates its power. Let's explore the visualization toolkit that makes this possible. Scatter plots of the first two principal components serve as the foundation, displaying each observation as a point in the reduced dimensional space. This simple yet powerful approach immediately reveals clusters, outliers, and the overall distribution of your data. In our Netflix example, this visualization might show distinct groupings of users with similar taste profiles that would remain hidden in the original high-dimensional space. Biplots take visualization a step further by superimposing the original variables as vectors on this same plot. These vectors indicate how each original feature contributes to the principal components, with longer vectors showing stronger influence. The angles between these vectors reveal correlations. Vectors pointing in similar directions represent correlated variables, while perpendicular vectors indicate independence. A biplot essentially provides a map of both observations and variables simultaneously, offering a comprehensive view of your data's structure. Loading plots focus specifically on these variable contributions, displaying how strongly each original feature influences each principal component. This helps identify which variables drive the patterns you're seeing. In retail analytics, for instance, a loading plot might reveal that purchase frequency and average order value heavily influence the first principal component, while return rate and browsing time dominate the second. For datasets with many variables, heat maps of the correlation matrix provide valuable context. These color-coded visualizations instantly highlight relationships between variables, showing which ones tend to move together and which operate independently. This context is crucial for interpreting what your principal components actually represent in real-world terms. The true value of these visualizations emerges when interpreting the patterns they reveal. Clusters in your scatter plot often represent natural groupings in your data, customer segments with similar behaviors, products with comparable performance metrics, or genes with related functions. Each cluster tells a story that might lead to actionable business insights. Outliers in these visualizations deserve special attention. Far from being merely anomalies to discard, they often represent unique cases that warrant investigation. In financial fraud detection, these outliers might flag suspicious transactions that don't fit normal spending patterns. In manufacturing quality control, they could indicate potential equipment failures before they occur. Different industries leverage these visualization techniques for specific purposes. Pharmaceutical researchers use biplots to understand relationships between drug compounds and their effects. Financial analysts create heat maps to visualize risk factors across investment portfolios. E-commerce platforms generate scatter plots of customer segments to inform targeted marketing campaigns. The tools to create these visualizations are readily accessible. Python libraries like Matplotlib, Seaborn, and scikit-learn provide comprehensive functionality for creating high-quality PCA visualizations. For those working in R, packages like ggplot2 and FactoExtra offer robust options for producing informative and aesthetically pleasing plots. When creating these visualizations, always consider the explained variance ratios we discussed earlier. They provide crucial context about how much information is retained in your visual representation compared to the original dataset. A beautiful visualization that only captures 20% of your data's variance might lead to misleading conclusions. Those variance ratios aren't just contextual footnotes, they're actually measuring something profound about your data. Think of them as the scoreboard that shows exactly how much information survives when you compress your dataset. When data scientists talk about explained variance, they're referring to the percentage of the original data's variability that each principal component captures. This metric forms the core of the fundamental trade-off in PCA, simplicity versus fidelity. With every dimension you remove, you're sacrificing some information in exchange for a more manageable dataset. The critical question becomes, how much information can you afford to lose? Calculating this ratio is surprisingly straightforward. After computing the eigenvalues of your covariance matrix, the explained variance for each component is simply its corresponding eigenvalue divided by the sum of all eigenvalues. This gives you a precise percentage of how much total variance each component accounts for. Let's look at a concrete example from water quality analysis. In this study, researchers found that the first principal component alone explained 32% of the total variance. The second component added another 22%, while the third and fourth components contributed approximately 13% each. Cumulatively, just these first four components captured a substantial 80% of the total information in the dataset, despite reducing the dimensionality dramatically. What's particularly fascinating is how this pattern repeats across diverse fields. In a music dataset analysis, the first principal component accounted for about 11.6% of the variance, with the second component adding around 8%. By the time you reach the third component, you'd captured approximately 25% of the variance. While this might seem less impressive than the water quality example, it still represents a substantial information preservation with minimal dimensions. The shape of these explained variance curves tells a story about your data's inherent structure. They typically follow what statisticians call a scree plot, showing a rapid initial drop-off where the first few components capture significant variance, followed by a long tail of components that contribute minimally. This visual pattern often reveals a natural elbow point where the curve flattens, suggesting an optimal cutoff for component retention. For determining how many components to keep, most practitioners follow a simple but effective approach. Retain enough components to reach a cumulative explained variance of 80-95%. This threshold varies by application. In exploratory analyses, 80% might suffice, while in high-stakes scientific research, you might aim for 95% or higher. What's truly remarkable is how few components are typically needed to reach these thresholds. Across various fields, from finance to genomics, studies consistently show that retaining just 5 to 20 principal components can preserve 80 to 90% of the original information, even when starting with hundreds or thousands of variables. Consider again our water quality example. Retaining just 4 components explained 80% of the variance, while expanding to 133 components would explain 99%. This demonstrates the diminishing returns that additional components provide, a key insight when balancing computational efficiency against information preservation. The implications for high-dimensional datasets are profound. When facing thousands of variables, you're often dealing with highly redundant information, variables that essentially tell the same story from slightly different angles. PCA excels at consolidating this redundancy, extracting the essential narrative while filtering out the noise. This brings us to perhaps the most critical decision in PCA application: where to draw the line. Set your threshold too high, and you're left with too many dimensions to be useful. Set it too low, and you risk discarding crucial information. The optimal balance depends on your specific goals. Are you more concerned with perfect data representation or with creating a simplified model that captures the essential patterns? The mathematical elegance of PCA might tempt us to use it universally, but this powerful tool has specific scenarios where it shines and others where it fails spectacularly. Think of it like using a specialized instrument, perfect for certain tasks, potentially destructive for others. Beyond finding the right threshold for components lies an even more fundamental question: is PCA the right tool for your analysis at all? What if applying this powerful technique to certain datasets could actually lead you to completely wrong conclusions, like using a hammer when you need a screwdriver? PCA assumes linear relationships between variables and works best with continuous data. This fundamental assumption means it excels with datasets containing numeric measurements that vary continuously, like sensor readings, financial metrics, or physical dimensions. When these relationships follow relatively straight lines on scatter plots, PCA captures the underlying structure efficiently. But here's where things get problematic. When your dataset includes categorical variables like product types, customer segments, or demographic groups, PCA's mathematical foundation begins to crumble. The linear transformations at PCA's core simply don't map well to the discrete nature of categorical data. Forcing such variables through PCA can create artificial patterns that don't represent real relationships. Consider a retail dataset with purchase amounts, continuous, alongside customer gender and product categories. Categorical. PCA might create components that seemingly show patterns, but these patterns could be mathematical artifacts rather than genuine insights. The distortion happens because PCA treats categorical variables as if they had numerical meaning beyond their labels. Interpretability presents another significant challenge. When stakeholders ask what your principal components actually mean, you're faced with explaining synthetic variables that represent weighted combinations of original features. This becomes particularly problematic in fields like healthcare or finance, where decisions need clear justification. While the first component in our earlier Netflix example had a reasonably intuitive interpretation, many real-world applications yield components that defy simple explanation. The non-linear limitation of PCA is perhaps its most significant blind spot. Many real-world phenomena follow complex, curved relationships that PCA's linear transformations simply cannot capture. Imagine trying to represent a spiral pattern with straight lines. No matter how many lines you use, you'll always miss the fundamental structure. This is where alternative techniques come into play. For datasets with complex nonlinear structures, methods like TSNE, T-distributed stochastic neighbor embedding, and UMAP, uniform manifold approximation and projection, excel at preserving local neighborhood relationships and revealing clusters that PCA might miss entirely. These techniques prioritize keeping similar data points close together in the reduced space, making them particularly valuable for visualization and cluster identification. When your goal extends beyond dimension reduction to understanding underlying factors, factor analysis offers a compelling alternative. Unlike PCA, which focuses on maximizing variance, factor analysis specifically seeks latent variables that explain correlations among observed variables. This makes it especially valuable in fields like psychology, market research, and social sciences, where researchers aim to uncover hidden constructs driving observable behaviors. Autoencoders represent yet another powerful alternative, particularly for complex data sets with non-linear relationships. These neural network-based approaches learn a compressed representation of the data by encoding it into a lower dimensional space and then reconstructing it. Their ability to capture complex patterns makes them particularly effective for image and text data where linear methods fall short. So how do you choose? Consider a decision framework that starts with your data characteristics and analysis goals. Ask yourself, are your variables continuous or categorical? Are relationships linear or nonlinear? Is interpretability critical? What's more important, preserving global structure or local relationships? For exploratory analysis of continuous variables with approximately linear relationships, PCA remains an excellent starting point. When working with categorical data or complex nonlinear patterns, techniques like TSNE, UMAP, or autoencoders will likely yield more meaningful results. And when you need to identify latent factors with clear interpretations, factor analysis often provides the clearest path forward. Now that we understand when to use PCA and its alternatives, let's shift from theory to practice. Behind the complex mathematics and technical considerations, PCA is quietly powering million-dollar decisions across industries from healthcare to retail, though executives might never mention terms like eigenvectors in their board meetings. Financial institutions have discovered that PCA can transform their fraud detection capabilities by identifying suspicious patterns hidden within vast transaction datasets. By applying PCA to financial metrics, banks can detect anomalous activities that would be impossible to spot in raw data. What makes this particularly valuable is how it reduces response time. Some institutions have cut their fraud detection timeline by up to 70% by focusing only on the most informative patterns rather than sifting through countless variables. The retail sector has embraced PCA for customer segmentation in ways that traditional demographic analysis simply cannot match. E-commerce giants apply this technique to purchasing history data to uncover the underlying factors that truly drive consumer behavior. Rather than grouping customers by age or location, companies identify natural segments based on latent preferences revealed through PCA. This leads to more targeted marketing campaigns that speak directly to customer motivations instead of superficial characteristics. In manufacturing, PCA has revolutionized quality control and equipment maintenance. Production lines generate thousands of sensor readings per minute, creating a dimension overload problem that makes traditional monitoring ineffective. By implementing PCA, manufacturers can detect subtle deviations from normal operating patterns before they become critical failures. This proactive approach to maintenance has allowed companies to reduce unplanned downtime by identifying which specific combinations of measurements actually predict equipment failures. Healthcare organizations are applying PCA to longitudinal patient data to understand disease progression patterns. Consider the remarkable efficiency gain in aquaculture operations, where researchers discovered that just 4 water quality parameters, identified through PCA, account for approximately 80% of the decision-making regarding fish survival conditions. The study revealed that dissolved oxygen influenced 32% of overall conditions, while pH levels contributed another 22%. By focusing resources on monitoring and controlling these key parameters, aquaculture operations can drastically improve efficiency while maintaining optimal fish health. What makes these applications transformative isn't just the statistical technique itself, but how it translates into concrete business value. When organizations deploy PCA effectively, 3 primary benefits emerge: operational efficiency, strategic insight, and risk reduction. Operational efficiency comes from focusing limited resources on what truly matters. Instead of monitoring hundreds of variables, companies can identify the handful that actually drive outcomes. This translates into more streamlined processes, reduced monitoring costs, and faster decision-making. A manufacturing plant that knows precisely which 4 sensor readings predict equipment failure can implement targeted maintenance protocols that cost a fraction of comprehensive approaches. Strategic insight emerges when PCA reveals hidden relationships in complex datasets. Retailers discovering that seemingly unrelated products share common principal components can redesign store layouts to increase cross-selling opportunities. Healthcare providers identifying latent patterns in treatment outcomes can develop more personalized care protocols based on the underlying factors rather than surface-level symptoms. Risk reduction happens when organizations gain visibility into complex systems through dimensional simplification. Financial institutions applying PCA to market indicators can better anticipate volatility by monitoring a few key composite metrics instead of trying to track hundreds of potentially noisy variables. This translates into more robust risk management strategies that remain effective even during turbulent market conditions. Despite PCA's remarkable impact on risk management, the most challenging dimension to reduce might be the gap between your technical understanding and your stakeholders' comprehension. Imagine discovering game-changing patterns in your data only to have your findings dismissed because you describe them as orthogonal transformations of feature space rather than the 3 factors driving customer decisions. This communication gap represents the final hurdle in leveraging PCA's full potential. You've mastered the mathematics, processed the data correctly, and uncovered valuable insights, but now comes the true test: translating these technical discoveries into a language that drives business decisions. Consider the all-too-common scenario. A data scientist proudly presents a scatter plot of principal components to executives, explaining eigenvalues and variance ratios, only to be met with blank stares and the inevitable question, so what does this mean for our business? The technical achievement becomes meaningless without effective translation. The art of communicating PCA results begins with powerful analogies. Rather than explaining the mathematical transformation itself, you might compare PCA to finding the best angle to view a sculpture, where the goal is to capture the most important features without losing essential details. This immediately makes the concept tangible to non-technical stakeholders, connecting it to their everyday experience. Visualizations serve as your universal translator. A well-designed scatter plot displaying the first two principal components can show executives how customer segments naturally emerge from the data without requiring them to understand the underlying mathematics. The visualization becomes a shared language between technical and business teams, allowing everyone to participate in insight discovery. When interpreting principal components, business-relevant terminology is essential. Instead of referring to principal component 1, describe it as the main factor influencing customer satisfaction. This simple reframing shifts the conversation from abstract mathematics to concrete business outcomes. For example, in a retail context, you might rename a component that shows strong loadings for purchase frequency, basket size, and promotional response as the customer engagement dimension. The step-by-step narrative approach proves particularly effective when presenting PCA results. Begin with the business problem, show the complexity of the original data, then reveal how PCA transforms this complexity into clarity. This progression helps stakeholders appreciate both the challenge and the solution without getting lost in technical details. The greatest communication failure is focusing on the technique rather than the insights it generates. Executives rarely care how you arrived at your findings. They care about what those findings mean for their decisions. Instead of explaining how PCA works, emphasize what the results reveal about customer behavior, operational efficiency, or market opportunities. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Creating a direct connection between PCA findings and specific business questions transforms your analysis from interesting to actionable. For instance, if your analysis reveals distinct customer segments based on principal components, immediately tie this to targeted marketing strategies for each segment. Show how understanding these underlying patterns can drive concrete business decisions and improve key performance indicators. One particularly effective framework involves translating your findings into a three-part narrative: the pattern you discovered, why it matters, and how to act on it. For each principal component or cluster revealed through PCA, clearly articulate, we discovered this pattern in customer behavior, which impacts these business metrics, and suggest these specific action items for your team. The ultimate test of successful communication is whether your analysis leads to action. An insightful PCA analysis that sits on a shelf has failed, regardless of its technical brilliance. By focusing on business implications, using familiar language, and providing clear next steps, you transform mathematical insights into strategic decisions. Mastering communication is only valuable when your analysis is sound, yet even the most elegant PCA implementation can be built on mathematical quicksand. Behind many failed data science projects lies a critical error that compromises validity while everything appears to be working perfectly. These hidden mistakes don't announce themselves with error messages. They quietly distort your findings, leading stakeholders down entirely wrong paths. The most pervasive mistake in PCA implementation is failing to standardize your data before analysis. When variables exist on dramatically different scales, think home prices in millions versus bedroom counts, The mathematics of PCA will naturally gravitate toward the variables with larger numerical ranges. This isn't because those variables contain more information, but simply because their values create more variance numerically. Without proper standardization, a variable measuring temperature in Celsius will contribute far less to your principal components than the same measurements in Kelvin, despite representing identical information. This scaling issue creates a particularly dangerous situation because your analysis will produce results that look completely valid. The mathematics works either way, but the components you extract will be dominated by whichever variables happen to have larger scales rather than which variables contain the most meaningful information. Your insights become artifacts of your measurement units rather than reflections of the underlying patterns in your data. Another prevalent misconception is assuming that principal components always yield straightforward interpretations. While the mathematical transformation is deterministic, the meaning of the resulting components isn't guaranteed to be intuitive. In many cases, components represent complex combinations of your original variables that don't map neatly to real-world concepts. Forcing interpretations onto these mathematical constructs can lead to misleading narratives about what's actually driving variation in your data. Many analysts compound this problem by blindly reducing their datasets to just 2 or 3 components without considering how much information they're discarding. While visualization constraints often push us toward two-dimensional representations, there's nothing magical about this number from an analytical perspective. Reducing complex data sets to an arbitrary number of components can leave critical patterns undiscovered and lead to incomplete or misleading conclusions. The appropriate dimensionality depends entirely on your specific dataset and the explained variance distribution across components. Some datasets might require 10 or more components to capture the essential structure, while others might be adequately represented with just a few. The key is making this decision based on the cumulative explained variance rather than convenience or visualization preferences. A fourth critical error involves applying PCA to categorical data without appropriate preprocessing. Since PCA is fundamentally designed for continuous variables with linear relationships, directly applying it to categorical features can produce nonsensical results. Categories like product types, geographical regions, or customer segments don't have inherent numerical relationships that PCA can meaningfully extract. When analysts ignore this limitation, they end up with components that suggest mathematical relationships between categories that don't actually exist. For example, PCA might position Northeast between Midwest and Southwest regions as if there were some natural ordering or distance relationship among these categories, creating an illusion of patterns that have no basis in reality. These pitfalls aren't just theoretical concerns, they represent very real risks to your analytical conclusions and the business decisions that depend on them. Imagine a pharmaceutical company using improperly implemented PCA to analyze drug effectiveness across different patient populations. The skewed results could lead to misallocated research funding or missed opportunities for effective treatments. To safeguard your analyses, implement consistent standardization protocols before applying PCA, particularly when variables exist on different scales. Take time to evaluate the explained variance when selecting component counts rather than defaulting to arbitrary numbers. Be cautious about forced interpretations of components, especially when they don't align with domain knowledge, and carefully consider whether your data is appropriate for PCA in the first place, particularly when dealing with categorical variables. Those standardization protocols aren't just technical formalities. They're the difference between insight and illusion. When a millimeter scale measurement sits alongside kilometer scale variables in your dataset, which do you think PCA will pay attention to without proper standardization? Let me show you something startling. Take the exact same dataset and run PCA twice, once on raw data and once on standardized data, and you'll get completely different principal components pointing in entirely different directions. This isn't a subtle difference, it's a fundamental transformation of what your analysis reveals. Consider this. When PCA operates on raw data, it naturally gravitates toward the variables with the largest absolute scales. The first principal component becomes effectively hijacked by whatever feature happens to use the largest units of measurement, regardless of its actual importance to the underlying patterns. It's mathematically inevitable. PCA seeks directions of maximum variance, and unstandardized variables with larger scales inherently contribute more to that variance. This mathematical reality creates a dangerous situation where the scale of measurement, not the importance of the variable, dictates which patterns PCA identifies. A temperature measured in Fahrenheit will influence your analysis more than the same temperature in Celsius simply because the numbers are larger. Housing prices in dollars will completely dominate bedroom counts in a real estate dataset. The shape of your data cloud fundamentally changes with standardization. Without standardization, your data might resemble an extremely elongated ellipsoid stretching primarily along one axis, the axis of your highest variance feature. After proper standardization, this same data cloud might reveal its true structure, perhaps multiple distinct clusters or relationships that were previously hidden. Standardization comes in different forms, each with distinct effects on your PCA results. Mean centering, subtracting the average from each feature, allows PCA to focus on variations around the center of your data cloud rather than absolute positions. However, this alone doesn't address scale differences. Full standardization Z-scores both centers the data and scales each feature to unit variance, ensuring every variable has equal opportunity to influence the principal components. The choice between using correlation and covariance matrices in your PCA implementation directly connects to standardization. When you use a correlation matrix as the basis for PCA, you're implicitly standardizing your variables. This approach ensures that each feature contributes equally to the analysis. In contrast, using the covariance matrix without prior standardization allows features with larger scales to dominate the results. This distinction becomes critical in fields like genomics, where expression levels of different genes might naturally vary by orders of magnitude. Without standardization, PCA would primarily capture the behavior of the most highly expressed genes while missing crucial patterns in genes with lower expression levels that might actually be more biologically significant. Visual examples make this concept crystal clear. When we plot unstandardized data, the principal components align almost perfectly with the axes of high variance features. After standardization, these same components often reveal diagonal patterns cutting across multiple features, showing how variables interact in ways that were previously invisible. To systematically approach standardization decisions for PCA, you should first assess the nature of your variables. Are they measured on comparable scales? Do differences in variance represent meaningful signal or arbitrary measurement choices? Is the absolute magnitude of a variable meaningful for your analysis, or just its pattern of variation? The answers to these questions should guide whether you standardize and how. Beyond optimization of data structure, the real power of PCA emerges when we integrate it into machine learning workflows. The carefully standardized components we've extracted become fuel for algorithms that can now operate with remarkable efficiency and accuracy. What if the difference between a mediocre model and a production-ready one isn't more data or a fancier algorithm, but simply how you prepare your features? This question reveals the often overlooked competitive advantage of PCA in the machine learning pipeline. High-dimensional data presents unique challenges for machine learning algorithms. When models encounter hundreds or thousands of features, they struggle with the computational burden and often fall victim to the noise hiding within that complexity. The algorithms can't distinguish between meaningful patterns and random fluctuations, leading to models that memorize training data rather than learning generalizable insights. PCA serves as a critical pre-processing step that transforms this chaotic, high-dimensional space into a structured, information-rich environment where learning algorithms can thrive. By injecting PCA into your workflow before model training, you're essentially providing your algorithms with a distilled version of the data where the signal has been separated from the noise. This integration is particularly valuable with algorithms sensitive to correlated features. Consider classification tasks where logistic regression or support vector machines are applied. These algorithms assume independence between features, an assumption frequently violated in real datasets. By transforming the original correlated features into uncorrelated principal components, PCA creates the ideal conditions for these algorithms to perform optimally. The benefits extend beyond theoretical improvements. In practical terms, models trained on PCA transformed data often demonstrate significant performance gains. Studies have shown that classification models using PCA preprocessing can achieve accuracy improvements up to 30% compared to those using raw, high-dimensional data. This boost in performance stems from PCA's ability to filter out noise that would otherwise confuse the learning process. The reduction in dimensionality also addresses the pervasive problem of overfitting. When models train on too many features relative to the number of observations, they learn patterns specific to the training data that don't generalize to new examples. By condensing the feature space through PCA, models focus on the most informative aspects of the data, resulting in more robust predictions on unseen examples. The computational advantages are equally compelling. By reducing dimensions from potentially thousands to just dozens, PCA dramatically decreases the training time for complex models. What might take hours or days to compute with raw data can often be completed in minutes with PCA transform features. This efficiency gain enables more rapid experimentation and iteration, a crucial advantage in competitive data science environments. Water quality assessment provides an illuminating case study of PCA's integration with machine learning. Researchers faced the challenge of identifying which parameters most significantly influenced fish health among dozens of water measurements. By applying PCA as a pre-processing step, they extracted key composite features that captured the essential variations in water quality. These transformed features were then fed into classification algorithms that predicted fish health outcomes with substantially higher accuracy than models using the original measurements. When implementing PCA in your machine learning pipeline, consider these best practices. First, always perform PCA on the training data only, then apply the same transformation to validation and test sets. This prevents data leakage that could artificially inflate performance metrics. Second, cross-validate the number of components to retain. The optimal dimensionality for visualization may differ from what produces the best model performance. Finally, consider using a pipeline object in your code to ensure consistent application of pre-processing steps across all data splits. The integration of PCA with clustering algorithms deserves special attention. Algorithms like k-means struggle with high-dimensional spaces where distance calculations become less meaningful. By first reducing dimensions with PCA, clusters emerge more distinctly in the transformed space, leading to more accurate groupings that reflect genuine patterns in the data. The difference between understanding PCA concepts and implementing them successfully lies in seeing the complete workflow in action. Have you ever wondered what separates amateur applications from those that deliver genuine business value? It's all in the details of execution, the systematic process that transforms raw, messy data into those aha moments that change how decisions are made. Let's consider what a complete PCA workflow actually looks like when professionals tackle a complex data set. While we've covered individual techniques and concepts, seeing how everything fits together in practice reveals the true art of dimensional reduction. Imagine you've just received a data set with hundreds of variables and thousands of observations. The relationships between variables are unclear, patterns are hidden, and stakeholders are waiting for insights. This is where a methodical PCA workflow becomes invaluable. The journey begins with exploratory data analysis, understanding what you're working with before applying any transformations. This critical first step involves examining the data set's structure, identifying correlations between variables, and analyzing the distributions of individual features. By visualizing relationships and calculating basic statistics, you develop intuitions about potential patterns that PCA might reveal. Preprocessing becomes the next crucial phase. Data scientists meticulously check for missing values, outliers, and inconsistencies that could skew results. The decisions made during preprocessing directly impact the quality of your PCA analysis, determining whether you'll uncover genuine patterns or merely artifacts of poor data preparation. Standardization represents perhaps the most critical technical step in the entire workflow. Professional analysts always ensure that each feature contributes equally to the analysis by centering the data around zero and scaling it to unit variance. This prevents variables with naturally larger scales from dominating the results, allowing PCA to identify the true directions of maximum variance. The actual implementation of PCA follows, often using libraries like scikit-learn in Python. A key decision point emerges. How many components should you retain? Experienced practitioners examine the explained variance for each component, looking for that sweet spot where you've captured sufficient information while still achieving meaningful dimension reduction. Visualization transforms abstract mathematical results into interpretable patterns. Creating scatter plots of the first few principal components can reveal clusters, trends, and outliers that were invisible in the original high-dimensional space. Loading plots show how much each original variable contributes to the principal components, helping to interpret what these new dimensions actually represent. What separates professional implementations from amateur attempts is the iterative approach to the entire process. When initial results aren't clear, experienced analysts don't hesitate to revisit earlier stages, trying different pre-processing techniques, adjusting standardization methods, or exploring alternative visualization approaches until meaningful patterns emerge. The culmination of this workflow isn't just a mathematical transformation, but actionable insights. In fields like aquaculture, this might mean identifying key water quality parameters that most influence fish survival. In music analysis, it could reveal the underlying audio characteristics that differentiate genres. These insights answer specific business questions and guide strategic decisions. The beauty of this methodical approach is its adaptability. Whether you're analyzing financial data, genomic sequences, or customer behaviors, the core workflow remains consistent while allowing for domain-specific adjustments at each stage. That adaptability extends to choosing the right technique for your specific analytical goals. Did you know that sometimes PCA might be the wrong tool entirely, despite its popularity? Factor analysis, often confused with PCA, operates on an entirely different assumption about what's actually happening in your data. While these two techniques appear similar on the surface, their fundamental premises create significant divergence in both application and interpretation. Factor analysis isn't just an alternative to PCA, it represents a completely different philosophical approach to understanding what generates your data. The mathematical distinction is crucial. PCA focuses on capturing the maximum amount of total variance in your dataset, but factor analysis specifically targets common variance, the portion of variability that variables share with each other. This seemingly minor difference leads to profoundly different interpretations of results. Conceptually, PCA is primarily a data reduction technique, transforming your original variables into new uncorrelated components. Factor analysis, however, operates as a latent variable model, assuming that unobservable factors are actually causing the patterns we see in our observable data. In essence, PCA describes your data, while factor analysis attempts to explain it. Consider a psychological study examining responses to a personality questionnaire. PCA might reduce dozens of questions into several components, representing different aspects of personality based on which questions vary together. Factor analysis would approach the same data set, assuming that underlying unmeasurable psychological constructs like extroversion or openness are causing people to answer certain questions similarly. The results from these approaches can differ dramatically. When applied to the same dataset, PCA might identify dimensions based purely on statistical variance patterns, while factor analysis could reveal groupings that align with established theoretical constructs. For instance, PCA might group personality traits simply by how much they vary together in the data, while factor analysis would group extraversion and sociability under a common factor because it assumes they're manifestations of the same underlying psychological construct. This distinction makes factor analysis particularly valuable in fields where researchers are trying to uncover hidden constructs that can't be directly measured. In psychological research, factor analysis helps identify latent traits like openness or conscientiousness by examining how observable behaviors correlate. Market researchers similarly use it to understand underlying consumer preferences by grouping related product attributes into meaningful categories. So when should you choose factor analysis over PCA? The decision hinges on your research goals. If you're primarily focused on efficiently reducing dimensions for visualization or as pre-processing for machine learning, PCA likely remains your best option. But if your goal is to uncover meaningful underlying constructs, especially in psychology, social sciences, or market research, factor analysis offers a more appropriate framework. The noise sensitivity of these techniques also differs significantly. PCA captures all variance in your data, including measurement errors and unique variance specific to individual variables. Factor analysis, by design, separates common variance from unique variance and error, making it less sensitive to outliers and measurement issues. A practical decision framework might look like this. Are you trying to identify underlying causal factors that explain correlations between your variables? Choose factor analysis. Are you primarily interested in dimension reduction while preserving maximum variance? Stick with PCA. Are your variables expected to be influenced by common factors that aren't directly measurable? Factor analysis will likely reveal more meaningful patterns. Beyond the basic PCA versus factor analysis decision lies an entirely different challenge. What if your data contains nonlinear relationships that traditional PCA simply can't capture? While we've explored how standard PCA excels at finding linear patterns in data, real-world datasets often harbor complexities that demand more sophisticated approaches. Consider an image recognition system trying to identify patterns across thousands of photos. The relationships between pixels rarely follow neat linear patterns. They form intricate, curved relationships in high-dimensional space. Standard PCA would flatten these nuances, potentially missing crucial patterns. This is where advanced variations of PCA enter the picture, each designed to overcome specific limitations of the standard implementation. Kernel PCA represents one of the most powerful extensions, specifically designed to handle nonlinear relationships in your data. By applying what mathematicians call the kernel trick, this technique cleverly maps your original data into a higher dimensional space where linear separation becomes possible. In image processing applications, kernel PCA has proven remarkably effective at recognizing patterns that standard PCA would miss entirely. The technique essentially transforms the data into a space where complex, curved relationships can be represented linearly. then applies standard PCA principles in this transformed space. When interpretability is your primary concern, sparse PCA offers an elegant solution. Unlike standard PCA, where principal components typically include contributions from all original variables, sparse PCA introduces sparsity, meaning many of the loadings are explicitly set to 0. This makes the results significantly easier to interpret, particularly in high-dimensional datasets where identifying a small subset of significant variables is crucial. Genomic researchers have employed this technique to pinpoint specific genes associated with diseases, isolating the small handful of genes that contribute most to the variance in their data, rather than dealing with complex combinations of hundreds of variables. Data scientists working with financial transactions or sensor readings often encounter another problem: outliers that distort standard PCA results. Robust PCA addresses this challenge by decomposing your data matrix into two separate components: a low-rank matrix capturing the underlying structure, and a sparse matrix that effectively isolates the outliers. This separation allows you to extract meaningful patterns even when your data contains anomalous values that would throw off traditional analysis. Finance professionals apply this technique for anomaly detection in transaction data, identifying potentially fraudulent activities without being misled by legitimate but unusual transactions. What about datasets so massive they won't fit into your computer's memory? Incremental PCA solves this challenge through a clever mathematical approach that processes data in smaller batches, updating the principal components as new information arrives. This makes it particularly valuable for online learning scenarios or when working with continuous data streams. Video processing applications leverage this technique to analyze footage in real time, updating their PCA models without needing to retrain from scratch with each new frame. The power of these advanced variations becomes clear when we examine their real-world impact. In water quality monitoring studies, researchers applied specialized PCA variations to identify the key variables affecting fish health. While standard PCA identified important parameters, the advanced implementations revealed subtler relationships between dissolved oxygen and pH levels that would have remained hidden under conventional analysis. These discoveries allowed for more precise environmental monitoring protocols that focused resources on the most influential parameters. Each of these specialized PCA variations shares the same fundamental goal as the original technique: finding the most informative dimensions in complex data. However, they accomplish this through sophisticated mathematical extensions that address specific limitations of the standard approach. The key is knowing which variation to apply based on your data's characteristics and your analytical objectives. Understanding the mathematical foundations of PCA is one thing, but translating that knowledge into code that actually works on your dataset is where many data scientists stumble. Did you know that a shocking number of PCA implementations fail not because of complex mathematics, but because of simple pre-processing mistakes that could be avoided with the right systematic approach? Let's bridge that gap between theory and practice with a practical framework you can apply immediately. The difference between theoretical understanding and practical mastery often comes down to 6 critical steps that transform abstract concepts into working code. First, evaluate whether PCA is appropriate for your specific dataset and analysis goals. Ask yourself, are your variables continuous and numeric? Do you suspect linear relationships between variables? Is maximizing variance capture your primary goal? If you answered yes to these questions, PCA is likely a good fit. However, if your data contains primarily categorical variables, or you're more interested in uncovering specific latent constructs, you might want to consider alternative techniques we discussed earlier. Once you've determined PCA is appropriate, focus on thorough data pre-processing. This crucial step begins with handling missing values through imputation or removal, depending on their prevalence. Identify and address outliers that could distort your results using robust statistical methods. Most importantly, standardize your data to ensure all features contribute equally to the analysis, regardless of their original scales. A practical framework for implementing PCA includes 6 essential steps. First, collect and preprocess your data, addressing quality issues and ensuring consistent formatting. Second, standardize the data to give all features equal opportunity to influence the results. Third, calculate the covariance matrix to understand relationships between variables. Fourth, perform eigenvalue decomposition to identify the principal components. Fifth, select the optimal number of components based on explained variance. Finally, project your original data onto these selected components to create your transformed dataset. Let's look at a reusable code template that implements this framework in Python. Python from sclern.decomposition import PCA from sclern.preprocessing import standard scalar, standardizing the data scalar, standard scalar, scaled data, and scalar.fit, transformed data, applying PCA, PCA, and PCA and components, comp2, principal components, PCA.fit, transform, scaled data. This simple snippet handles the core functionality, but effective PCA implementation requires careful validation as well. Use scree plots to visualize the explained variance distribution and determine where adding more components yields diminishing returns. Cross-validate your component selection by training models with different numbers of components and comparing their performance. Examine component loadings to ensure they make sense in your domain context. Documentation is another aspect of PCA that separates professional implementations from amateur ones. For reproducibility and knowledge sharing, document your entire process in detail. Include a description of your dataset, all pre-processing steps applied, your rationale for choosing specific parameters, visualizations of explained variance, and your interpretation of the principal components in domain-specific terms. This documentation enables others to understand, validate, and build upon your work. Best practices for implementing PCA involve ensuring that your data is properly mean-centered and scaled before analysis. Use scree plots to visualize the explained variance and determine the optimal number of components to retain. Document each step of your PCA process thoroughly, including the rationale for decisions made during the analysis. This approach creates a reproducible workflow that others can follow and understand. As we conclude our journey through principal component analysis, it's worth reflecting on why this technique has endured as a cornerstone in data science. Despite the emergence of more complex methods, PCA remains widely used across neuroscience, finance, and environmental science. Its enduring relevance stems from how it bridges mathematical elegance with practical problem solving. When you apply PCA in your work, remember that its true value isn't in the mathematical transformation itself, but in how it transforms your understanding of the data's fundamental patterns. The technique empowers you to penetrate the fog of high-dimensional complexity and discover the underlying simplicity. What separates exceptional PCA implementations from mediocre ones is a systematic approach that emphasizes evaluating the appropriateness of PCA for your specific dataset, careful pre-processing with special attention to standardization, thoughtful execution of each PCA step, thorough validation of results, and clear communication of findings to stakeholders. By following these practical steps, you transform PCA from a theoretical concept into a powerful tool that delivers actionable insights. This perspective, seeing through complexity to identify what truly matters, is what distinguishes exceptional data scientists. PCA offers more than just a technical solution. It provides a lens through which you can develop this essential analytical perspective.